it's almost as if I forgot how to do this. I have to remember all the things I do in order to get this ready. So, I mean, the slides are fine. I think the slides are fine. Um, I'm making changes to my layout. Um, so I'm trying to make space up in the corner for me, making space for myself. Um, and then we're changing topics, right? College algebra and pre-calculus math. I'm doing math here. My PhD is not in physics or in math, it's in STEM education, which means I can teach physics and math. So that's what I'm doing over here. The cat's definitely here. She's having snack emergencies at my feet, and I'm just it's always rusty to get back in front of a mic and running through these slides. So yeah, average rate of change. That's good stuff. Rise over run. Change in the output over change in the input. And I don't know, it's a good topic to start back in on. It's easy, I think. Um, it is a foundation for, calculus, really. But in college algebra, we just start with the little stuff like can you do slope of a line, and then can you kind of do the same thing on something that's not a line? It's not a line; it's a parabola. You want up here too? No? All right. Um, so you can do that, and then you can plug numbers into the function, right? You could plug numbers into the function and find the rate of change over two values of input. And then look at this, algebra. Then we move to college algebra 2, where we're doing a little bit heftier work with algebra and algebraic expressions that we plug into the function. And so the algebra becomes a rational function, right? And so working with all that algebra can be intimidating and frustrating for students, especially for attention to detail. That's where I see students go weird on this. You can plug in something easy like just a letter, but then you can do something more complicated with a number and a letter. Oh. And then this one's the fun one where you can do different functions. Here's a rational function. And then you can just use straight variables into the function and then get a composite function, right? Or something like that. Yeah, not a composite. It's just an operation on a function. And then you can talk about calculus and the rate of change. That's what I was saying earlier. Like calculus, the rate of change. You get to the fundamental theorem of calculus where you start taking limits, right? Take a limit. When you take a limit of this rate of change expression, then it creates a tangent line at a point on a graph and gives the instantaneous change. And in the video, I'll talk about average speed versus instantaneous speed as a specific example in physics of this concept mathematically. I haven't picked out an example problem yet. It hasn't come to my intuition what's going to be a good thing to do here. I'm not ready to do limits. Having said that, limits come into calculus, but I think I'm just going to talk about end behavior, right? Like when you take a limit, when you let something equal infinity, what does that do to whatever the rate of change is? And how does that relate to slope on a graph? That's the right thing I need to do because slope on a graph, that's a good, the cat's here. There's her tail. Hi, kitty. At certain points, like at minima or maxima, the rate of change, the instantaneous rate of change, the slope of that tangent line is 0. It's a flat line. So there's the first application of derivatives in there. See, I said derivative, we start with college algebra and then we move through some stuff and all of a sudden I'm talking about derivatives. And so exciting material, exciting application of an easy idea of the slope of a line. So I thank you for watching my channel.